In this final video on aromatic substitution, we're going to look at multi-step synthesis and some of the types of planning that you need to go through as you devise a synthetic route to turn a benzene derivative into a far more substituted benzene derivative. Okay? All right, so I've outlined 4 principles here, followed by a 5th one that we'll add later. Okay, first understand that you have to get the right orientation of substituents to obtain the maximum credit. And for now, we're going to assume that an ortho-para director will give you what you need, whether it be ortho or para. If you want ortho, you'll get ortho. If you want para, you'll get para. In reality, we're going to see that monosubstituted activated benzenes usually give you a lot more para than ortho for steric reasons in the real world. Okay? There are several problems with the Friedel-Crafts alkylation that we might not have covered back then, but now that we understand about how multiple substituents factor in, we can now look at some of those problems. Okay? All right. We've already covered the first one here, rearrangements, because it's a carbocation or because the reaction involves carbocations, you can often get rearrangements. Okay? All right. Another issue is that the product you get of the Friedel-Crafts reaction is actually more reactive than your starting material. This is because you've added an alkyl group to your benzene ring, and since it's now got one additional activating group on it, it's now more reactive than it used to be. So you can have a lot of problems with overalkylation. And finally, issue C is that the reaction does not work for anything less activated than a halobenzene. Okay, problems A and B are not an issue in the Friedel-Crafts acylation. We don't get rearrangements there usually, and the Friedel-Crafts acylation puts a C double bond O directly on the ring, so our ring becomes less reactive when we do the Friedel-Crafts acylation. However, issue C is still a problem with the Friedel-Crafts acylation. Okay, so this issue C here, just want to reiterate that it's only the Friedel-Crafts reactions that have this limitation. None of the other reactions in this chapter have this limitation. You can nitrate deactivated rings, you can sulfonate deactivated rings, and you can halogenate deactivated rings just fine. Okay? All right, whenever we see an aromatic ring with a COOH group, the way we're usually going to make that is to perform a side chain oxidation of an alkyl benzene like we saw in the previous chapter. We're going to treat an alkyl benzene with sodium dichromate, aqueous sulfuric acid in heat, or potassium permanganate in heat. Okay, so this group here, COOH, even though it's putting a C double bond O on the ring, does not usually come from the Friedel-Crafts acylation. It comes from the side chain oxidation in most cases. All right. When we see a vinyl group attached, or an alkenyl group directly attached to an aromatic ring, it's usually going to arise through treatment of the alkyl benzene with NBS and light to give you the halo alkyl benzene, and that's going to be followed up by an E2 reaction to give you the alkene. So it's we can't really put this group on directly by the Friedel-Crafts reaction, because remember that was restricted to alkyl halides or the acid chlorides that you need in the Friedel-Crafts acylation. Finally, I'm just going to say that this is not all we're going to see about aromatic substitution. We are going to, in future chapters, cover other reactions that will substitute a benzene ring, and we'll see how some of the reactions we look at in the future are going to actually solve this ortho-para issue. We'll introduce several reactions in later chapters that give you almost exclusively ortho and never para. We'll also see that some rings are too activated, and we have to tone down their activation to actually get Friedel-Crafts, or to get electrophilic aromatic substitution reactions to proceed the way we want to without extensive over substitution. All right, so what we're going to see here is a series of 4 synthesis problems. Hopefully they cover most of the issues that you would likely see in a multi-step synthesis. We've covered one classic problem, how to avoid rearrangements and making alkyl benzenes through doing the Friedel-Crafts acylation followed by reduction in previous parts of this chapter. Now we're going to look at some other types of problems. All right, so let's look at this problem right here. We're going to outline a series of reactions that accomplish the indicated transformation. What you should do when you see a reaction like this is just look at what's ortho, para, or meta to whatever. So we know that ortho para directors are activating, and they're really going to serve as controlling groups in most cases. And in this situation here, what we see is that bromine is ortho para to the best electron donating group. We're going to install that one last. And acetyl, what is acetyl? Just remember that from the previous chapter, that group there is acetyl, abbreviated AC. Okay, and that's also ortho para to the best electron donating group, and we're going to install that one after we install the ethyl group, because the ethyl group will direct it exactly to the right place. And in the real world, since we're going to get more para than ortho, we're going to put the acetyl group on before we put the bromine on. Okay. All right, so this is the synthesis that we would use. We would want to first install add the ethyl group to get ethyl benzene. Okay, we'd have to be a little bit careful here because the ethyl benzene is more reactive than benzene. We probably have to use a large excess of benzene, not a problem since it's a relatively cheap compound. Okay. Next, we're going to do the Friedel-Crafts acylation, and here, ethyl group, ortho para director, and activating, so it's going to make this go either para right there or ortho here. And remember, we typically do get more para than ortho with monosubstituted benzenes. So this reaction here, the Friedel-Crafts acylation with acetyl chloride and aluminum chloride, is very likely going to proceed in high yield to produce predominantly this product, accompanied by a little bit of the ortho isomer. All right. Okay, now when we brominate this, we have an ethyl group and an acetyl group. This is an electron donating group. This is an electron withdrawing group, so this is going to control the orientations. This is an ortho para director, so any incoming electrophile is going to go ortho para to the ethyl group. Para is blocked, so it can only go ortho. And this final step is going to give you the final product. So this 3-step synthesis would probably produce this product with a very high degree of selectivity. Okay, let's look at this one. Here we have several groups on our benzene ring. What we see here is that all of the groups are actually deactivating groups right now. The most activating group here would be chlorine, and what we see here is that we have some things that are ortho to it and some things that are meta to it, so it's not going to be an effective controlling group at all. All right, so notice that everything is ortho para relative to the COOH group, and that's going to be the key to this synthesis here, is using the precursor to that group as the controlling group for all the other things. all the other groups that are on this benzene ring. So what you notice here is that all these groups are orthopara to the COH. So we're going to perform a side chain oxidation at some point, but before we perform that side chain oxidation, we have an electron donating orthopara director right there. So that's going to be the key to controlling everything. Okay. All right. So we're going to try and keep it as an alkyl group while we're installing all of the other things. All right. So here's our synthesis. We're going to perform the permanganate oxidation last, or we could use the chromate oxidation as well, and that's going to turn our ethyl group into a COH group, okay? All right, now, while this is an ethyl group, as stated before, it's going to control where all these other things go, okay? All right, so everything is orthopara to the ethyl group. And that's so all we have to do is install the substituents. The sulfonic acid is para, and remember that that's where we get more substitution when we have a monosubstituted benzene. So we're going to add that one first, since that's going to be para, and that'll make the other ones choose the ortho position. Okay. All right. So we're going to nitrate this compound here. That's tri-substituted benzene. Okay. Yeah. So this is a tri-substituted benzene. We're going to nitrate it, and the nitro group should be here again. The ethyl group all throughout is an orthopara director, and it's going to send our reaction exactly where we want it, or it's going to make our group go exactly where we want it to go. Okay? All right. And the previous step, again, this ethyl group is the controlling group, and para has already got something there. So when we add chlorine, we're going to want to add that ortho. So we're going to add chlorine here, which is ortho to that, and nitro here, which again is also ortho to our orthopara director. All right, we're going to sulfonate first, sulfonate after adding the ethyl group. Okay, so this is the para position, and the SO3H is going to go predominantly para. And when we do this reaction, we're going to get a little bit of the ortho compound, but mostly the para compound. Okay? And the first thing we would want to do is install the ethyl group. Okay? Because here we install the group that's going to control the position of all the others. All right? This is really the best synthesis we can come up with. All right, we'll call this step 1, step 2, and step 3, and step 4. It's a 4-step synthesis. What are our alternatives? We could have 4 before 3. Okay, I wanted to do 3 first because I wasn't as severely deactivating the ring as much as I would by nitrating it, so I think it would go at higher yield if you do 3 first than 4, but that's still, both of them would work. Okay, if we tried to do any of these chlorinations or nitrations before the sulfonation, we probably wouldn't get high selectivity for the ortho position, but we would get some of the right product. As far as like adding the ethyl group later, actually all of these groups here except chlorine deactivate this ring so much that we could not really do a Friedel-Crafts reaction. So it's very wise to do the Friedel-Crafts reaction first. Benzene is actually more activated than any of the rings except for ethylbenzene, the product of the very first reaction. Okay, let's look at this one. And this one, one of the things you'll note in this chapter is that we don't have any reactions listed that replace a hydrogen on a benzene ring with an oxygen. Therefore, in this one, it looks like our best way to get in that ethoxy group is to replace the chlorine in a nucleophilic aromatic substitution reaction. All right? Okay, so how would we go about converting chlorobenzene into that tri-substituted benzene? All right, so the last thing we would want to do is to perform a nucleophilic aromatic substitution. This particular product down here is actually quite activated for the nucleophilic aromatic substitution because in the ortho position we have a nitro group and in the para position we have an acyl or a C double bond O. Both of those are pretty good electron withdrawing groups, so we would expect this chlorine to be relatively easily displaced in this two-step nucleophilic aromatic substitution reaction. 2 steps in the mechanism, 1 step in the actual synthetic operation. Okay, all right. And what you see here now is that we have the acyl group, para, and the nitro group, ortho, so we're going to take advantage of the fact that chlorine is an ortho-para director, and we're going to add the acyl group first since we usually get more para than ortho. Okay, so our second to last step is going to be nitration of this group here. And when we look at this, the chlorine is the strongest electron donating group, or we could say the weakest electron withdrawing group, because remember, it's not actually an electron donating group at all. So it's the fact that it's controlling the orientation is due to the fact that it's even though we have 2 electron withdrawing groups, it's chlorine is or halogens are classified as weakly electron withdrawing, so it's electron donating relative to the other group on here. Okay, so even though both of them are electron withdrawing groups, chlorine is not as electron withdrawing as this C double bond O group. Okay, and in our last step, we're just going to do in our first step rather, we're going to do the Friedel-Crafts acylation, and we're going to do the Friedel-Crafts acylation first, since for 2 reasons. Okay. Para is typically favored over ortho for monosubstituted benzenes, and the fact that if we put this nitro group on too early, we actually might deactivate the ring so much that it won't do a Friedel-Crafts reaction anymore. Okay, all right, and finally we'll do this last synthesis problem here. This one's kind of interesting. About half the reactions do not come out of this electrophilic aromatic substitution chapter. They come out of previous chapters. Okay. All right, so I want to highlight the specific point here that phenols have a pKa of about 10. We don't really cover how to turn an alcohol into the corresponding ether until a later chapter, but what you can see here is that if the pKa is 10 and we treat it with sodium hydroxide, we would actually get a deprotonation reaction that would give us an alkoxide, and that would do an SN2 reaction. So we're going to deprotonate followed by SN2 to convert the OH to OCH3. Okay, so we're going to do that. We're going to take advantage of the high acidity of the phenol group when we do that transformation. All right. What you note here is that we have an alkenyl group on our ring. Okay, and we can't really install those directly through the Friedel-Crafts reaction. The best way to do this is to do the Friedel-Crafts alkylation, then do an NBS oxidation followed by an E2. Okay, so our last step here, the best last step we could have would be an E2 reaction on this halide right here. Okay, so this bromine here is tertiary and would definitely prefer to do an E2 over an SN2. Okay, all right, we're going to turn this compound where we have just a hydrogen right here into the corresponding bromide by treating it with NBS and light. All right, we're going to chlorinate here. And remember that if we look at naphthalene, there are two rings, but this ring on the right is activated, and this is not activated or deactivated. It really doesn't have anything on it, but this one over here is just loaded with activating groups. So a moderately good activator, an OCH3, and a weakly activating alkyl group, this isopropyl group right here. All right, so if we treated this compound with chlorine and FeCl3, we would expect the chlorine to go ortho to the strongest electron donating group, which is this group right here. This is our strongest electron donating group. All right, in our in our second step, we would just take this methyl ether right here and treat it and subject it to the Friedel-Crafts alkylation using isopropyl chloride. Here we have actually a rather interesting conundrum here. Do we add there or do we add there? Remember, in naphthalenes, that the one position is more activated than the two positions, so we expect that this position, which is para to the OCH3, would be more activated than this position over here, which is ortho to the OCH3. Okay? All right. And finally, we'll make the ether, we'll convert the phenol to the ether in the very first step. Just look at a couple of hypothetical reorderings here. Could we form the methyl ether, which we're doing in step 1? Could we do that later? Hypothetically, yes, but probably you wouldn't want to do that. What we're going to find out when we study phenols is that phenols are too activated, and it's hard to stop these electrophilic aromatic substitutions at just the addition of one entity, particularly a reaction like the Friedel-Crafts alkylation, where the product is more reactive than the starting material. So we would probably want to tone down the reactivity of the phenol early. That's a consideration that will be talked about much later in the class when we look at phenol specifically. All right, could we chlorinate before the Friedel-Crafts alkylation? Well, actually you couldn't, because remember, like we said before, in naphthalenes, you prefer to substitute at the one position, which is the position immediately adjacent to the benzene ring, because you get better resonance stabilization of carbocations by attacking the one position. So if we chlorinated first, almost certainly we would get the chlorine in the wrong place, okay? All right, so it's very likely that the product of this reaction would be this, and this is undesired. Okay, so this is the last slide in this video, and this is the last of the slides in electrophilic aromatic substitution. Okay, so as I stated at the beginning of this video, there are more reactions that we'll talk about in the organic chemistry that substitute the benzene ring, predominantly compounds that involve nitrogens on the benzene ring. Okay, when we talk about amines, we'll talk about an actual new way to accomplish aromatic substitution in that chapter. Okay, all right, so that'll be